Yeah.
Hello and welcome to our short presentation of our project at the Hegel Lab this semester. Ingmar and I looked into quasicrystals and how we can generate pictures of them using the so-called cut and project method. And we created a web page with interactive tools which should give the reader a intuitive sense of how this method works and how the pictures are generated. We start with an introduction page where we talk about quasicrystals and why they are important for physics when they've been discovered, and then have a sections about tilings so that the reader understands the mathematical concepts to understand the patterns we're creating. And we just start by talking, okay, these are tilings, they can be periodically, and we have an example on the first page, which are just these regular polygons forming a tiling, and you can try out with the polygon with 3 sides, 4 sides, and 6 sides to see how they fill the plane and how this naturally can be thought of as a crystal. We also mentioned the cut and project method, which will be introduced on the following pages. So our personal way into understanding the cut and project method was via the Fibonacci tiling, or more to be more precise, the application of the cut and project method on the Fibonacci tiling. We briefly explained the cut and project method and then let the reader of the page play around with this interactive tool to see how, in the case of the 2D Fibonacci tiling, the pictures are generated. So you can see a small text, and then you have this tool on here. You can play around with the angle of the affine linear subspace. You can play around with the thickness and the offset to see how this generates pictures and get a sense for the workings of the cut and project method. So after the reader is through this, with this, we get to the centerpiece of our work on the cut and project method, and especially the centerpiece of our work, our programming work. You can also already see on the right side we have this beautiful picture of a Penrose tiling, which is, as we all know, the most famous example for a quasicrystal, for a aperiodic tiling. So this is briefly explained, and also it's briefly explained how we have to choose the dimension and the affine linear subspace to create a Penrose tiling. And then you can actually do the same thing you did on the page before and play around with these sliders to do the same thing, but only seeing the pictures that are generated. So first of all, you can zoom in and out. You can move along the x-axis. You can move along the y-axis, and you can change the offset of the affine linear subspace down here. Let me just, okay, you can see, you can change the offset to get different results as on the page before. So what was kind of a problem for us was that if we wanted to create larger pictures, the computing time would go up. So we decided to make smaller pictures, and if the reader decides that they want to see a larger frame of the Penrose tiling they currently look at, they can click on this button down here. For example, we have this. Then they can click on this button, wait for a brief period, and get a bigger picture, as you can see here. And then they can move around here and look at it. Yeah. And at the end, we also have a small gallery where you can revisit what you've just done and look into it again. So thanks for your attention. Maybe play around with the tool for a bit. And yes, thank you very much.